Hello, welcome back. So in the last couple of units, we've gone ahead and studied Kirchhoff's laws as they apply to batteries and resistors, and gone ahead and done a whole bunch of exercises just to make sure that we're very thorough in our understanding of Kirchhoff's laws as they apply to circuits which have batteries and resistors. But actually, there's another circuit element that we have studied in the previous chapter, which is a capacitor. And so it behooves us now to ask what happens when we have circuits which have combinations of batteries, capacitors, and resistors in them. And that's what we're going to go ahead and study in this unit and the next one for a while. Now, I'd actually point you all to some very nice YouTube videos. So there's a very nice YouTube video available on this website out here. So please go ahead and feel free to visit it. It deals with capacitors and how capacitors can be charged or discharged. That might be a useful thing to watch. And so with that, let's go ahead and now study what happens when you try to charge up a capacitor. So here we have on the top a circuit, and in this circuit you can see that we have a source of EMF, namely a battery, and we have a capacitor and a resistor. Now, as soon as the switch A is thrown, namely as soon as switch A is turned upwards so that it makes a contact, you have a circuit like the one shown in the left bottom panel. So what's going on in this circuit in the left bottom panel? Initially, of course, we realize that the charge on the capacitor is essentially 0 and 0 on both its plates, but that doesn't last for long. Why does it not last for long? The answer is that as soon as you throw the switch, some current begins to flow. In fact, you wouldn't be able to charge up the capacitor unless current flowed in this circuit. So you have a charge of plus Q on the positive plate of the capacitor and minus Q on the negative plate of the capacitor. And of course, the current flow actually goes through the resistor R and gets back to the battery. So let's go ahead and ask very simply if we can write out Kirchhoff's law for this situation. So we see that if we start, for example, here, and we go through the battery in the clockwise direction, namely going in this direction, then we have a voltage rise given by E. Okay? Then we go all the way around here, and we go here to the capacitor, and we realize that the capacitor has been in the circuit for a little bit, so it has been charged up by a little bit, so it has a charge of plus Q and minus Q on its plates. Therefore, there is a voltage difference of Q divided by C. Okay, where C is the capacitance of the capacitor. And notice that as we traverse the capacitor in this direction, we're actually going from its positive plate to its negative plate. Therefore, we should have a voltage drop given by minus Q divided by C, where Q is the charge on that capacitance. And then, of course, we go around the circuit and come back to its original location. And in doing so, we traverse the resistor in the direction of current flow. So we have a voltage drop given by minus I times R. And that is equal to 0. And we can write this equivalently as let me go ahead and remove the scratch. So we can write this as E minus Q over C is equal to I times R. This tells us that initially, when the charge on the capacitor is exactly 0, then we have an amount of current through the circuit given by I0, an initial amount of current in the circuit. We're referring to, of course, the circuit in the left lower panel, which is actually equal to E divided by R. So notice that initially what we have happening out here, and I'll go ahead and erase some of the things that we've drawn on this circuit just to make it more visible. So initially, what we have happening in this situation is a situation where the amount of current flowing through the resistor is exactly equal to the amount of current that would have flowed through the resistor had the capacitor not even been present. In other words, if you imagine a simple situation where the charge on the capacitor is zero, then you can imagine that the total current flowing through the resistor is just the same as the current flowing through the resistor if this had been just a simple circuit with the battery and the resistor and nothing else in place. So we see that initially this circuit behaves very much like a circuit that has a battery out here and has a resistor out here. Okay? So we see that initially, if the EMF in the battery is E and the resistance is R, then this circuit would have a current I, which is equal to E over R. And even in this capacitor circuit, we have the same amount of current. So it tells us that initially, when the capacitor is instantaneously thrown into the circuit, this capacitor behaves like a closed circuit. In other words, this capacitor is actually letting current get through. Now, why is current actually getting through? Current is actually getting through because some current comes from the positive plate of the battery, it goes here, and it gets wedged onto the positive plate of the capacitor. And of course, an equal and opposite amount of negative current is built up on the negative plate of the capacitor, which means that some amount of current is actually flowing away from the negative plate of the capacitor. So this is what explains to us why when a capacitor is instantaneously thrown into a circuit, it behaves like a closed circuit. Let's also go ahead and understand this from the viewpoint of the Kirchhoff's law that we have asserted above. So we see that at t is equal to 0, we have a situation where the charge on the capacitor is exactly equal to 0. And as a result, we see that the current in the circuit, if we put Q is equal to 0 in either of the two Kirchhoff's law assertions that we have above, then we see that the current I in the circuit is exactly equal to I0, which is equal to E divided by R. In other words, the current flowing in the circuit at time t is equal to 0, the current flowing through the resistor in the left bottom panel is exactly the same as the current flowing in this circuit, which actually didn't even have a capacitor to begin with. So we see that as soon as a capacitor is thrown into a circuit, it behaves like a closed circuit. So we have a closed circuit effectively. Now, what happens a long time later? Namely, as t tends to infinity, we have a situation where the charge on the capacitor keeps building up. Now, as the charge on the capacitor keeps building up, eventually we will have a situation where the EMF of the battery exactly balances off Q over C, namely the voltage on the capacitor. That's to say that E is equal to Q over C, and in that case, the left-hand side of this equation is exactly 0, which means that the current is exactly equal to 0. So this tells us that at a much later time, Q actually becomes equal to the capacitance C times the EMF of the battery itself. And when that happens, the voltage across the capacitor exactly balances off the voltage across the battery. And when that happens, there's no further voltage drop available, so there's no further voltage available to drive the current through the resistor in this fashion. So we see that at a later time, at a much later time, we have zero current in the resistor, which basically means that at a much later time, the capacitor behaves exactly like it would if you had just two simple plates with nothing going between them, namely the capacitor behaves like an open circuit. Okay, so we have this final realization that initially the capacitor behaves like a closed circuit, since it's completely uncharged initially at time t is equal to 0, it lets any amount of current that needs to flow through to go ahead and flow through, and therefore it behaves like a closed circuit, namely it behaves like this circuit. But that doesn't last for long, because charge starts building up on the capacitor, and therefore the capacitor also contributes some of the voltage in the circuit, and therefore eventually the charge builds up on the capacitor to the extent where the voltage across the capacitor exactly balances the voltage across the battery, and then the capacitor basically behaves like an open circuit. So once the capacitor is fully charged, the current in the circuit is exactly equal to 0, and the potential difference across the capacitor is just equal to the potential difference across the battery. Okay, so this gives us our fundamental insight, which is that a capacitor that is instantaneously thrown into a circuit behaves like a closed circuit. However, a long time later, the same capacitor behaves effectively like an open circuit. So with this, let's go ahead and try to understand the circuit that we have just analyzed. But this time we want to understand the evolution of the circuit at all possible times, not necessarily at the initial time and the final time. So let's go ahead and give ourselves a blank transparency, or transparency which has minimum amount of stuff written on it. And we're told that initially the charge and the voltage on the capacitor is what? And initially the charge on the capacitor is exactly 0. So the charge on the capacitor is exactly 0. And because the charge on the capacitor is exactly 0, the voltage on the capacitor is also exactly 0. Okay? So initially, the full extent of the voltage of the battery is indeed, when this switch is closed, out here, initially the full voltage of the battery is exactly applied across the resistor. So we say that the initial voltage across the resistor is E, and therefore the current flowing across the resistor initially is just equal to E divided by the resistance R. The question is, what is the final charge on the capacitor? So we realize that eventually the charge builds up on the capacitor to the point where the voltage across the capacitor is exactly equal to the original EMF of the battery. When that happens, we can say that the final charge is just equal to C times the EMF of the battery itself. And we understand that if we have current flowing in this direction, okay, in the direction that is just shown in this circuit, then this current will go ahead and contribute towards building up the positive charge out here. So we can assert that I is actually equal to dq by dt. I is of course always equal to dq by dt, but it is important to understand that when we assert it in this formula, what we're essentially saying is that the current is equal to the rate of increase of charge on the plates of the capacitor. So with this understanding, we can go ahead and write out our Kirchhoff's law. So let's go ahead and start at this point and go through the battery, essentially going from its negative plate to the positive plate. So we have Kirchhoff's law telling us that E is the voltage rise across the battery. Then we go through this part of the circuit and this part of the circuit. So we're traversing the resistor in the direction of current flow. So we have minus I times R. And then we're traversing this capacitor in this direction, namely we're traversing it from its higher potential plate, namely its positively charged plate, to its negatively charged plate. So we have a voltage drop given by minus Q divided by R. Now realize that we can actually go ahead and write this So we realize that this total is equal to 0. Now this is equivalent to going ahead and writing E minus Q over R. I'm sorry, Q over C. I should have written Q over C, which is the voltage drop across the capacitor. So I have Q over C. And here too, I should have had Q divided by C, which is equal to R times I. But in place of I can go ahead and use this expression where I can assert that all the current that is flowing in this given circuit goes to build up charge on the capacitor. So the current is equal to the time rate of buildup of charge on the capacitor. So I'll actually go ahead and erase the I out here, and in its place I will go ahead and write dq by dt. Notice that right here we see that we have the makings of a differential equation. In other words, the right-hand side has something times dq by dt, and the left-hand side has E, which is a constant, C, which is a constant, and Q, which is the only variable. So I can actually go ahead and write this as, so I can write this equivalently as being equal to So I can write this equation as being equivalent to C times E minus Q divided by C, and this is in fact equal to R times dQ by dt, but I can actually go ahead and bring the R out here, and therefore I write this as dQ by dt. Now let me go ahead and massage this equation and write it in a slightly better form. So I can write this equation as being equal to dq divided by q minus c times E, and on the other side I have minus dt divided by RC. Notice that all terms that are associated with Q have been brought to the left-hand side of this equation, and all terms that are associated with the time t have been brought to the right-hand side of this equation. Now the reason for doing that is obvious. We realize that at time t is equal to 0, we have Q is equal to 0. At some general time t, we have a charge given by Q at that general time t. So we can now go ahead and write this as an integration from 0 to the general charge Q of dQ divided by Q minus C times E, and that is equal to minus of the integral from 0 to time 0 to time t of dt divided by RC. Now this is very easy to work with because we realize that dq divided by q minus ce, the integration of that is just natural log of q minus ce. So this tells us that we have to have natural log of q minus c times e as the integral on the left-hand side, and this has to be integrated with the limits going from 0 to capital Q, and on the right-hand side we have minus t divided by RC. So we can go ahead and write this as natural log of q minus c times e divided by minus c times e is equal to minus t divided by RC. And now the obvious thing to do is to actually go ahead and take the exponentiation on both sides. so as to get rid of the natural log. So let's go ahead and erase off this expression that we've obtained and instead write a different type of expression. So we erase off this expression out here, and in its place we actually go ahead and write Q minus C times E divided by minus C times E is actually equal to e raised to minus T divided by RC. And then it's very easy for me to massage this equation and actually write it as our final desired equation, which is that Q is actually equal to C times E times 1 minus e raised to minus T divided by RC. This is in fact an expression for the charge as a function of time in the capacitor, and we see that when time t is equal to 0, this is 1 minus e raised to 0, which is 1. So we have an initial charge on the capacitor which is exactly equal to 0. As time t tends to infinity, e raised to minus t over RC tends to 0, and so we obtain a final charge which is just given by C times E, where E is the voltage of the battery. Now notice that this is an expression for charge as a function of time, and if I wanted the current I as a function of time in this situation, I can actually go ahead and obtain that quite easily by differentiating this expression with respect to time. So this tells us that we can actually obtain the current as a function of time also, and that's exactly what we obtain out here. So this tells us the charge as a function of time is actually building up till it reaches the final charge, which is just given by the capacitance times the EMF across the battery. And we realize that this buildup of charge as a function of time takes place in such a way that there is a characteristic time associated with it given by RC. RC is in fact the time that it takes for 63% of the charge to build up. So in other words, 63% of the charge is built up in an amount of time given by RC, and of course, proportionally, we see that the charge slowly and gradually reaches this asymptotic value that we had initially deduced. We can actually go ahead and take our expression for the charge Q as a function of time, which is just given as C times E times 1 minus e raised to minus T divided by RC. And we can actually go ahead and differentiate this guy with respect to time. So we can obtain I as a function of time is actually equal to dq by dt. And then that just gives us E divided by R times e raised to minus T divided by RC. You can go ahead and do the differentiation a little bit offline. And that actually tells us that the current is initially large and substantial and is given by just the current that we would expect in a resistor which is put into a closed circuit. Eventually, the current decays to 0, and the current decaying to 0 indicates to us that we have, at a very late time, the RC circuit behaves like an open circuit. In other words, the capacitor behaves like a closed circuit component initially, and at a very late time later, it behaves like an open circuit. So this basically reinforces exactly the same things that we have seen before. Now, the next thought question basically asks us, is it usually best to charge up a capacitor with a shunt resistor in the circuit? Now notice that capacitors have this tendency that they can actually go ahead and get charged up very, very fast, and they can go ahead and discharge very, very fast also. Now what happens when a capacitor discharges very, very fast? The answer is that all of the charge on that capacitor will try to go through whatever circuit it can find. And that means that if you have a capacitor that is allowed to discharge very, very fast, it can discharge as fast as it wants, which basically means that it can essentially produce a very large current. So a capacitor can actually produce a very large current when it is getting charged up without a shunt resistor. The shunt resistor was essentially the resistor R that you saw in the previous circuit, and a capacitor can actually discharge very rapidly if it is not provided with a shunt resistor. So we see that in that situation, the current I can become very large, and therefore the current I can burn out whichever circuit it is trying to kind of get through. So we realize that it is not optimal to basically charge up or discharge a capacitor without having at least some amount of resistance in that circuit, because the presence of the resistance in that circuit essentially means that if R is non-zero, then the time constant over which the capacitor charges or discharges is given by RC, and if R is non-zero, it means that it will essentially charge and discharge only over a finite amount of time. And that's actually why we call it an RC circuit. RC means that the time constant is just proportional to the resistor times the capacitor. So we now understand why it is always a good idea to have at least some shunt resistance in a circuit when charging up or discharging a capacitor, because if you didn't have that, you would basically generate unusually large current flow, which would burn out the circuit that you're dealing with. So our job as professors at Notre Dame is to basically give you good advice. And so the good advice and also the good points that you can get via this thought question basically all refer to the fact that whenever you're charging or discharging a capacitor, please do use a shunt resistor. We'll do the next two thought questions in class. Okay? Let's go ahead and move on and now deal with a situation that is exactly the opposite. So in the first part of this unit, we saw how to charge up a capacitor. Now we're going to essentially learn how to discharge a capacitor. So imagine, if you like, that we placed a charge of plus Q0 and minus Q0 on this capacitor C, and the switch is open, and we instantaneously go ahead and close the switch. The answer is that the voltage on this capacitor is just given by Q0 divided by C. That is just from the definition of a capacitor as being defined as the charge divided by the voltage. Therefore, you get the voltage as being the charge on the capacitor divided by the capacitance of the capacitor. So this is the initial voltage of the capacitor, and all of that voltage becomes visible across this resistor as soon as you throw the switch. So the amount of current flowing through the resistor initially is just given by the initial voltage that is visible across the resistor divided by the resistance. And so we can essentially go ahead and put this formula for V0 into this formula and obtain this as the initial current in this circuit. Now realize something. We have a current. Let's focus on the lower panel. We have a current that is flowing in this direction, and as this current flows, this current is basically draining the original charge on the capacitor. So we can actually say that I is minus dq by dt, where we're thoughtful about the fact that what we're referring to by way of dq by dt is actually the time rate of change of charge on the plates of the capacitor. Okay, so this current is serving to drain off the charge on the plates of the capacitor, which is why we have this minus sign out here. So with that understanding, we can actually go ahead and write Kirchhoff's law. So let me go ahead and clean up the circuit at the bottom, and then we'll actually go ahead and assert Kirchhoff's law going in this direction. So we realize that now we're traversing from the negative plate of the capacitor to the positive plate of the capacitor. So we have a voltage rise given by Q times C. Then we're traversing the resistor in the conventional direction of its current flow. So we have a voltage drop of IR. And those are the only two circuit elements. So we can essentially say that this thing is a complete expression of Kirchhoff's law for this particular circuit. Now we'll go ahead and put I is equal to minus dq by dt in order to obtain this expression out here. And with this expression given, we can actually write dq by dt on one side and take everything else to the other side, which basically tells us that we have dq by dt is equal to minus 1 over rc times q. Notice that the rc, which is the time constant that we found in the previous problem where we were charging up the capacitor, also shows up in this problem where we're essentially discharging the capacitor. Notice that if this shunt resistor had been amazingly tiny, what would happen is that you would have immense amounts of initial current flow in the circuit, and therefore you might actually blow the circuit. Now, you have actually seen an example of that, and I will remind you of it all over again when we get to that appropriate place in the narrative. So now we realize that we have massaged our equation so that we have dq by dt, namely the time rate of change of charge on the plates of the capacitor, being equal to minus 1 over rc times q. In other words, the charge is actually being drained from the plates of the capacitor because the current is draining that charge away and sending that charge through the resistor. Notice that the capacitor initially had a lot of electrical energy because it was charged up, and all of that electrical energy is essentially flowing by way of the current through the resistor, and the resistor is basically going to dissipate this energy as heat. So that is also something to be mindful of. So with this, we can essentially take the previous expression that we had and write it in the following fashion. So we realize that we will go ahead and take the previous expression that we had, which I will just repeat out here as being equal to dq by dt is equal to minus 1 over rc times q itself. So what we do is we basically take this q out here into the denominator on the left-hand side. So I obtain dq divided by q. And on the right-hand side, I take this dt that I have and I move it over to the right-hand side. So I get minus 1 over rc times dt. This process is called separation of variables. So what we've essentially accomplished is that we've taken everything that is associated with q on one side and everything that is associated with the variable t on the other side. So everything that is associated with the variable q is taken to the left-hand side, everything with the variable t is taken to the right-hand side, and there's nothing else. Everything else in this equation is just a constant. So we can now go ahead and say that we want to integrate from an initial charge of q0 at time t is equal to 0 to some general time charge of qt at a time t. So we essentially go ahead and integrate this guy. So we go from q0 initially to some general q at some general time t, and we have dq by dq is equal to minus integral from 0 to t of dt over the constant rc. So this essentially tells us that we have natural log of q at a general time t divided by the original charge q0 as being equal to minus t over rc. And if I take exponentiation of both sides, this essentially gives me q at a general time t is equal to q0, which is the original initial charge on the capacitor when it was fully charged up, times e raised to minus t over rc. So notice that again, we see the same combination of r times c as the time constant over which the capacitor is actually discharging. If we want to find the current I, we realize that I is actually equal to minus dq by dt in this instance because actually q refers to the charge on the capacitor itself. So we can go ahead and take this expression that we've obtained out here, or equivalently this expression, and go ahead and differentiate it with respect to time and put the minus sign appropriately. And this actually tells us that we have Q0 divided by RC. Notice from the previous transparency that Q0 divided by RC is just the initial current flowing through the resistor. And that current, we realize, is actually going to go ahead and decay exponentially with time. This is only natural because the initial current is the largest because the voltage across the resistor is the largest. But as the capacitor keeps getting drained, there's a smaller and smaller amount of voltage across the resistor, and so the current in the circuit decays, as does the charge on the capacitor. So this shows you the decay of charge on the capacitor. In other words, this is actually a plot of Qt, which is actually equal to Q0, the initial charge that you put on the capacitor, times e raised to minus t over RC. Okay? You can go ahead and differentiate this current to be able to plot out the charge. But now let me go ahead and remind you of the demo that you have seen, where we took this gigantic oil-filled capacitor which had a capacitance of 0.5 microfarads. Now, micro might seem like a small thing, but in the world of capacitors, microfarad is actually referring to a giant humdinger of a capacitor. And this capacitor was actually charged up to an initial voltage of 4,000 volts. And then we went ahead and suddenly, rapidly discharged it through an extremely puny resistor with just 10 ohms. So the resistor was acting like a shunt resistor, and you can actually see that this resistor was very tiny compared to typical resistors that you might have. And this shows you the perils of actually discharging a capacitor through a very tiny resistor or no resistor at all. In other words, what happened in that demo that I showed you in class was that you actually went ahead and fried the resistor, and you fried the resistor basically because you generated such a large current in the circuit that R times I squared produced a lot of heat in the resistor, and that basically caused the resistor to explode. So we see that we can actually go ahead and quantify some of the things in that demo that we did with the oil-filled resistor or oil-filled capacitor and the very tiny resistor. So we actually now can go ahead and evaluate the charge on that 0.5 microfarad 0.5 millifarad capacitor. So millifarad, I'm sorry. MF refers to milli. If it were micro, it would have been mu. So we had a 0.5 millifarad capacitor, and a millifarad capacitor is very big in the world of capacitors. So we actually can go ahead and say that what is the charge on the capacitor to begin with? We have charged it up to a voltage of 4,000 volts, so we can actually go ahead and take the capacitance of the capacitor, which is just 0.5 times 10 raised to minus 3 farads, that's millifarads, 10 raised to minus 3 is milli, times a voltage of 4,000 volts. And if we do this multiplication, we get an answer of 2 coulombs. Now, 2 coulombs is actually a very substantial charge to be putting on a capacitor. And we saw that the time constant, R times C, is basically equal to the 10 ohms for the resistor times the 0.5 times 10 raised to minus 3 farads for the capacitor. And we saw, therefore, that for this particular circuit, the time constant was amazingly tiny. So we're taking this gigantic amount of charge and we're draining 63% of it through the circuit in an amazingly tiny amount of time. This actually allows us to gauge the initial current in the circuit, and we've already obtained this formula. I0, the initial current in the circuit, is just equal to Q0 divided by RC. So in other words, the potential across the capacitor is just Q0 divided by C. And since this entire potential is initially seen by the resistor, this potential divided by the resistance R gives us the initial current I0 in the circuit. So this tells us that if we go ahead and put our C in the denominator and put Q of 2 coulombs in the numerator, we obtain a whopping big amperage. In other words, we have a gigantic amount of current flowing through this circuit for a very brief amount of time, and as a result, the power dissipated in the resistor is just equal to R times I squared. And you can imagine that this puny little 10 ohm resistor that we had in our demo had absolutely no chance because it had 0.4 times 10 raised to 3 amperes of current coursing through it, and this was more power than the resistor could dissipate as heat, and therefore the resistor basically chose to blow up instead. So we see that we have a, a charge. The charge in this problem evolves so that it diminishes exponentially. And that's this expression out here for Q as a function of time. And we can actually go ahead and realize that 5 times 10 raised to minus 3 seconds later, the charge on the capacitor was diminished by 1 e folding. 10 times 10 raised to minus 3 seconds later, the charge on this capacitor was diminished so that it was just 2 times e raised to minus 2, and 15 times 10 raised to minus 3 seconds later, the charge on the capacitor was just 2 times 10 raised to minus 3, 2 times e raised to minus 3, and e raised to minus 3 can actually be quite a large number, so the charge had basically drained away. Most of the charge on the capacitor had basically drained away very quickly in about 10 to 15 seconds. 10 to 15 milliseconds, I'm sorry. Now let's go ahead and just get a brief glimpse of where people use this sort of situation. So you have essentially a picture of the Z machine, which is which has been built and is operational at Sandia National Laboratories. I've actually been in this room, but not when they were sparking it up, because nobody is allowed to go in this room when the capacitors are all being charged up. And so what you have out here is one set of capacitor banks out here. Then you have all of their energy quickly and rapidly transferred to another set of capacitor banks out here. And then even more rapidly, they basically transfer all that charge to the third set of capacitor banks out here. So you're going from a slower capacitor, which only charges and discharges slower, to a relatively fast capacitor in the middle, and to an extremely fast capacitor at the end. And once you have all the charges transferred to these extremely fast capacitors, what they do is basically they drive this entire current through this tiny little fiber out here. And this fiber is actually a fiber of deuterium and tritium. So it's actually H2 and H3 mixture. And this fiber, which is supercooled, actually is solid, and it acts like a little resistor. So it acts like an amazingly tiny resistor that is connected to an amazingly large capacitor. And so you have an amazingly gigantic amount of current flowing through it. They say that it is 10,000 times or 1,000 times the energy of a lightning bolt in 1 over 20,000th of a time over which that lightning bolt might strike. And what that does to this little fiber of deuterium and tritium out here is that it sends a gigantic current through that little fiber, thereby producing a gigantic magnetic field around that fiber, and we will learn about that later on. And this magnetic field basically compresses this fiber, basically trying to heat up the deuterium and tritium to the same temperatures that you would have in the center of the sun. And the point of this experiment that they're doing at Sandia is to actually go ahead and take these guys and make them convert into helium, because we know that the sun is also a gigantic nuclear reactor that is taking hydrogen and burning it and turning it into helium and thereby producing energy. So the promise of the Sandia machine, if it ever succeeds in self-sustaining itself, is that we'd have a self-sustaining fashion of producing helium out of hydrogen, and in doing so, we can essentially extract a limitless amount of energy which we can use to power our cars, our houses, and so on and so forth with almost no environmental impact. Of course, this is maybe 20, 30, 40, I don't know how many years away into the future because this is very futuristic technology, but let's hope it comes about. So with this, let's move forward. So I essentially want to point out to you that that time constant tau, which is equal to RC, is actually the time that it takes to either charge up the capacitor to 63% of its maximum, or if you're discharging the capacitor, then that same time constant is the time that it takes to discharge the capacitor. And that sort of question actually plays out again in this thought question that you see out here. And this then brings us, so we'll go ahead and address this thought question in class again. And this thought question then brings us to the final transparency in this unit, which essentially reminds you of the same things that we started with, namely an uncharged capacitor that is put into a circuit initially behaves like a closed circuit. Closed circuit because it allows any amount of current to flow through without any voltage drop in it, and that is in fact because when the charge on the capacitor is zero, the voltage difference across the capacitor plates is exactly zero. And therefore, any amount of charge or any amount of current can get through that capacitor with zero voltage change across the ends of the capacitor when that uncharged capacitor is initially put into a circuit. So initially, it behaves like a closed circuit. So that is the important message out here. Now, after that capacitor has been in a circuit for a long time later, it basically behaves like exactly what it is. A capacitor is just two conducting plates that are separated by a certain gap, an air gap, and you know that air is a very good insulator. It won't let charge flow through. So unless of course there's dielectric breakdown, that air gap basically behaves like an open circuit, and therefore a long time later the capacitor basically behaves like an open circuit. In other words, current cannot get through regardless of the voltage that is applied across the capacitor. Of course, by then the capacitor has been charged up so that it has the same voltage across its ends as the battery. So with this, I will essentially thank you very much for your attention. I hope you learned a lot about the nuances between capacitors as they're initially thrown into a circuit and how they behave a long time later. I hope you've learned how to charge up a capacitor and how to discharge a capacitor safely with the help of a shunt resistor. What we're going to do in the next unit is do lots of quantitative problems that make sure that we understand the concepts that are described in this unit and are able to use them to solve quantitative problems. So with that, I will thank you all very much and hope to see you in the next unit. Thank you and see you later.